Today we will review chapter 10, the DC to DC converters is basically control rectifiers. So, the rectifiers, if you would be using a diode, the output voltage is pretty much fixed, input is fixed and output voltage is fixed. Output voltage depends on the input voltage, that's the fixed. But for control rectifiers, uses thyristors, whereby one could control the conduction time of the devices of thyristors and control the output voltage. This type of controller are used for variable DC output voltage, wherever it needs that variable DC output voltage, like driving DC motors or like charging a battery or any other applications where you need a variable DC from a fixed application. And they are used for large power applications, many applications you need that one. Like maybe you need to have some the heating, like I got weldings or DC supply, you need a large DC voltage, a variable DC voltage from a fixed AC voltage. And we will, this is again for course EL 4244 power electronic. One of the first question asked for you, the average output voltage control rectifier will be will decrease with the delay angle. That's of course that if this is the output voltage what we expect normally, like a diode rectifier is a half wave rectifier, the output voltage would be this will be the output voltage if this is delayed by alpha. That means that if you make the delay to 0, there will be maximum. If you make the delay to 90 degree, it will be the here. If you make the delay to somewhere 180 degree, you expect a 0 there. That may decrease with the delay angle. The next question asks for your RMS value of the output voltage. What is the RMS value? The RMS value of this waveform, like if you have this waveform, this is the waveform you got. It's a sine wave. This is the sine wave. Normally you have the root mean square goes 0 to 2 pi, 0 to say 0 alpha to pi, basically alpha to pi, sine theta square d theta, root of the mean of the square. This is the square, this is the VM, this one's mean of the square, root of the mean of the square, and then you got VM square. You have to make a VM square, root of the mean of the square there, root of the mean of the square. The mean, you got a square, you got a root, you take the mean, and that's the mean of that, and take a square, root mean square. Okay, that is the one you're giving me the voltage that you're going to find out that this is going to be increased always. Root mean square value is always the higher than the DC value. If you have a pure DC, then the RMS value and then the DC value will be the same. On the other hand, if you got any other distorted waveform, root mean square value is always more than the average value. The instantaneous output voltage in this particular case would be positive, because the output voltage will be equal to that one. It will be always a positive voltage depending on the triggering angle. This will be the positive there. The instantaneous thyristor current can only flow through this thyristor, will be only positive. No current can flow in the opposite direction. The average output voltage, you can calculate it out. If this is given like 170, if your VM is 170, they ask you, then find out the average voltage. You can find out that the average voltage will be equal to 0 to pi, 0 to alpha to pi, VM sine theta d theta 1 by 2 pi. That is the one you got, that one. Okay, that is the one you got. You can find it out. If your alpha is alpha is 90 degree, you can calculate out that. Cosine non-alpha is 0. Cosine alpha will be 0. That will be equal to 2 pi by VM. That's what you got. Now the question comes there. This is the RMS value. If you can also find the RMS value also, if it needs to is ask for the average value, you can calculate out alpha equals to 90, cosine 90 is 0, then you can find 2 PM by 5. That is the one I expected to calculate out. And the instantaneous output voltage will be, in this particular case, that is a highly inductive load. That means that the highly inductive load means that the current will be always continuous. If the current is continuous, that the current will be flowing either through one or two of them, and then or the current will be flowing through 3 and 4. That will be, the current will continuously flow, because that will be current will be swinging for positive and negative. the current will be always on the input current will be swing, but this current is always a continuing. This current, the output current is a DC there, but the thyristor current half of the time will carry a 1, half of the time will carry a 1 there. That means the instantaneous output voltage would be positive or negative depending on that, depending on that what you are, because that's why if you got a highly inductive load, that the output voltage could be positive or negative depending on that, the alpha you have. Like on the previous note, we say that if you got a full wave rectifier, it could be the both way. We're going to see in a minute. It could be positive and negative depending on that the delay angle you have. That the highly inductive thyristor will conduct for what? If you got a conduct for, this will be 180 degree, this will be 180 degree. That means each thyristor will conduct for 180 degree. 1 and 2 will conduct for 180 degree. 3 and 4 conduct for 180 degree. That is the answer. Like average output voltage in this particular case, you can do that 0 to alpha pi sine theta d theta. This will be alpha to pi. There will be 2 of them. There will be 2 pulses because the full wave. That's why you multiply by 2. This will be 2 Bm by cosine alpha. The DC current you can find, the RMS current will be root mean square alpha to pi, B square sine over there will be 2 of them, 2 by 2 pi. This is the Vs, because that's not a surprising there. Because if your output is, output will be like this, output will be like this, or output will be like this or that, is the RMS value is the same. That you can calculate it out if that a VM is a 170, the delay angle is 90, you can find out the average output voltage will 100 inductive load. You can find it out how much will be the average output voltage. Obviously, if there is a cosine is 90 there, this will be somewhere there. Okay. Input power factor. The input power factor of that one, you can look. There is a derivation of the input power factor for a single phase rectifier, for the rectifier, control rectifier for highly inductive load. This is, I believe in example 10.1. Please look through that example 10.1. The power factor will be equal to the power factor is equal to 2 square root of cosine of the alpha, depending on the alpha there. That means that it will be the minimum input factor will be when alpha equal to 90 degree. 90 degree, 90 alpha 90 is equal to almost 0. Okay, that's the minimum there. And now on this other one, input power factor, the input power factor of the cosine function of the delay angle. That's true. Input factor is the cosine of the delay angle. That's why whenever the input factor is cosine. The highly inductive input power factor cosine of the delay angle. We already said that. Operating mode. What will be operating mode? The highly inductive DC converter operated in the first quadrant and the second quadrant. This could be the VI plot. The current could be current will always go this direction, positive direction. The current could be positive and then or negative. Okay, the current is always positive. Current is always positive. The current will always go through this load in this direction because this is a rectifier. But the voltage could be either positive or negative, either positive or negative, depending on that if this is a 180 degree or more than 80 degree. That's why this converter can give you a positive voltage or a negative voltage, but the current will be always positive. Like you are in the motor, you are driving, you are supplying a motor voltage. It will run a positive direction, or you can turn the motor in the other direction if you put the other way, depending on the angle that could operate in the first quadrant and then the fourth quadrant. The RMS value of the output voltage is that RMS value of the output voltage with a highly inductive load Vm by they always if this is this this waveform, this is the Vm by square root of 2. That's what it is. RMS value of the sine wave is Vm by square root of 2. That's what it is. The peak-to-peak voltages would be equal to the peak line-to-line voltages. Peak line-to-line voltages. If you have a if you got a three-phase rectifier, the peak voltage, the V peak, will always equal to square root of 3 the Vm. This is the Vm. If you got the line-to-neutral voltages, whatever the line-to-neutral voltage you have, this will be, if you got a 120 volts, RMA, and the value, the peak value will be equal to. It's not 170 is the peak value. and the RMS value is whatever the RMS value, it will be that, the square root of root 3 multiplied by 2 3, because the three-phase supply multiplied by three-phase square root of 3. And the RMS value, the RL log, each thyristor conducts for how many degrees? Each thyristor conducts, there are 3 of them, 360, 120 degree will conduct for that. And the triggering of the thyristors will be at, the triggering thyristor is phase shifted with 90 degree and 90 degree, 60 degree. Why? 1, 2, 3, 4, 5, 6, 360 divided by 6 of them is a 60 degree. That means first one will be, this will be like a 60, they delayed, the next one is 60, next one is 60, next one is 60. There are 6 of them, but one will be like, it's delayed. First one is started from there, it will be 120, then the next one will be delayed by 60, 120, the third one will be delayed by another 60. That's why you go for that. This is the way. Look for. Please look for that. The figure. It explains the figure for that. The triggering angle for that. The thyristor. Please look at the figure 10.3. At the delay angle. The delay angle normally, what is the reference? Is zero crossing of phase voltage. You look through the phase voltage. Whatever the phase voltage you have, that's this. The delay zero crossing of that one. Remember, the line and phase are the difference. The line where the phase voltage is between the line A to neutral, and the line voltage, phase voltage is between the phase A to line to neutral, and the line A to B between the line voltage. Triggering sequence normally 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, and then come for 1. That's the sequence. The ordering is done 1, 3, 1, 3, 5, and then 2, 2, 4, 6. When you see a numbering of the thyristors, you always see the top 1, 2, 3, and the 2, 4, 6, so that the triggering become 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6. Remember, there are 6 of them. There is a 6 combination: 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6, 6 and 1. There is a 6 degree. This is the sequence you have to drive. And the average output voltage of this 3-phase rectifier, you can draw that. There is on the equation you derive there. I believe on that. Average output voltage of a 3-phase supply is in equation 15. You can calculate it out. What will be the average output voltage? Will be between, depending on this alpha, or the 0 to the power 180 degree alpha. If it is 180, it could be -2. That's where the answer is M. Now that average current of each thyristor, you got there are average current of 3 thyristor. There are the DC, the output is 3 there. Output is a fixed, like a DC for highly inductive load. There are on the top, if you look to the 135, there are 3 of them. That means this current must be shared by 3 of them. This would be 1/3. And then look, RMS value of this, there will be the 3 of them, but it's the RMS value. It will be by square root of 3, because it will be the RMS value square root of 3. Then average current of line supply voltage. The line will be equal to the line. If you got a line there are 3 lines: line A, line B, line C. And then if you got the line A, line B, line C, the total current will be the same. That means it will be IA divided by 3, and that's divided by 3 lines. There will be 3 lines there: line A, line B, line C, 3 there. It will be share this current, but look at that. You see, there is nothing nothing is 1/3, and that means the none of the above. Okay. The RMS value of each thyristor current will be equal to, there are 2 of them. It will be covered. 2 of them will go for that, and the line RMS current will be like, if you look to the figure, the RMS value of this figure, like 10.3. If you look to this, the line current, there are two. Each current will have this positive and negative. Like if you look through this one, you got a positive and negative there, or this is the line current, line A. You got a positive. It's a 1 here, 1 here. There are 2 of them. Okay, there are 2 of them, but the average is 0. But the RMS value will be 2 of them square root of 3. Okay, there are 2 of them. There will be 2 by 3. There are 2 positive pulse and a negative pulse. That will be square root of 3. The initial load current, that is it. That you can load that. If you look through that, if you look to the book, there is an initial expression for the continuous current of that. a three-phase with RL current. If you look through that equation, the equation 1021, and that is it. That's a long equation. Like it gives you the VL is given there. VL is given there. Line voltage is given. You have to look at the phase voltage there. And then line A to B is given there. Then you go to 60 hertz, you go to L, you go to R there, E equal to 0. They ask you to find the initial current of that. That's typically 1021, and it's very difficult to do it by hand calculation. That I would encourage you to use the mathcat files to look into the answer. I believe the answer will be the answer. The average current, to do the average current is more complex than this. Is the current you have, and you have to integrate that current from 0 to within 180 degree, and then take an average, and that's the instantaneous average over the one. That will be much useful to mathcat or MATLAB or any other file. The answer, I believe, will be like this. Again, try to use that the software tool. Frequency of the output voltage in this particular, there will be 6 pulses there. If you look through that, the output waveform, of that, the figure 10.3, there are 6 pulses you expect that, within itself. The frequency of that will be 6 times that one. Now, many times you put them in a series of parallel. This is the connected in series. Selected current to increase the voltage limit. If this converter can give you 1 voltage, the other one give output, you got to double the voltage you can have. Sometimes you connect them. Now, in this particular case, there will be like 12 pulses. This will be 6. This will be 6 there. That will be 12 pulses. You're going to get some pulses there. There will be 12 pulses you expect in the output. Now, this is the end of the chapter. Chapter and the plus. Please review those. The theory, and also that the workout examples in the book using the mathcat file. Please do that. I think that's the end of that presentation.